We're watching ocean waves. As we watch the ocean waves, there are two things that we can observe. One is the frequency of the ocean waves, and one is the wavelength. The wavelength of the ocean waves is the distance between the peak to peak of the waves. So if we measure this distance, we'll have our wavelength. Now, when we talk about light, the wavelength of light are so small that we have to use something really, really tiny. The unit in this case is going to be nanometer. A nanometer is 1/1000th of a meter. So if you cut the meter in half and you keep cutting it in half 1 billion times, you end up with a nanometer. The frequency of the ocean waves is how many waves we get in unit time hitting the beach. So in the case of light, the unit is hertz, and that's the number of waves every second. There's quite a few waves every second when we talk about light, because it travels so fast. It travels at the speed of light, which is 300,000 kilometers per second. Light is the only wave that we know of that if you know the wavelength, you can figure out the frequency. If you know the frequency, you can figure out the wavelength. This is the spectrum of light. Now, when we talk about light, we also talk about frequency and the wavelengths of light. Gamma rays have the highest frequency amongst all the light waves. And so gamma rays do not penetrate the Earth's atmosphere. So up here we have whether or not they penetrate the Earth's atmosphere or not. Here we have the name. Now the name is really not that important because it's the frequency and the wavelength that is more important. Regardless, when we talk about gamma rays, these are the highest frequency waves in nature and they have the shortest wavelengths. As we go towards the radio waves on the other end of the spectrum of the electromagnetic radiation, we see that the wavelengths get longer and longer and the frequency drops. And so when we talk about gamma rays, this is the highest frequency and the shortest wavelengths in nature. Next we have X-rays. There's a variety of X-rays. We call them hard X-rays, soft X-rays. Soft X-rays have a longer wavelength. Hard X-rays have a shorter wavelength. They would penetrate your body, and that's when we take X-rays of your skeleton. Ultraviolet light has longer wavelengths than X-rays, and the frequency now is dropping. So as we go towards the radio waves, the frequency is dropping, but the wavelength is getting longer and longer. Next we have the visible light. And the visible light make up what we see as a human being. The shortest of all the visible lights, the shortest wavelengths, are the violet. The longest wavelengths in this case will be the red waves. After red, we have what we call infrared, beyond red. This is basically heat. And heat also travels at the speed of light. So do microwaves, so do radio waves. And so the longest waves in nature are the radio waves. We choose them for communication because they travel over the mountains, over the hills, over our houses, and so on. So this constitutes the entire electromagnetic spectrum that is possible to see in nature. Now there's two ways we can get a spectrum of light. That means we can spread the light so we can see the constitutes light. What constitutes light, visible light, starts with violet all the way to deep red. There's two ways of making a spectrum. One is to use a prism. So a prism is an easy way to do it. You have white light going through the prism. As we know, the waves slow down and the red slows down the least. Violet slows down the most, so the waves spread out. But there is one other way to spread the light and get a spectrum of light, and that's to use what is called a diffraction grating. And this diffraction grating basically is either a mirror or a glass that light can pass through. In this case, we're using a transmission grating where light can pass through. A grating is basically a piece of glass. On this piece of glass, there's a lot of cuts, so the light can go through the clearing and it avoids places where it's not clear. So this black lines here that we see is where the light cannot go through. When the light goes through a small opening, it has a tendency of spreading out. Now it spreads to the left in this case and to the right, and when it does, the red waves spread the most and the violet spreads the least, so that's how we spread them. When the sound goes through a small opening, it also spreads out. This is called diffraction.